Hello. Hi, everyone. Hey. Hi. My name is Boris. I'm an engineering manager at Cloudflare. I've been at Cloudflare for about 8 months now. And before that, I was the founder and CEO of a startup called Baseline. We used to build observability for serverless architectures. And we were acquired by Cloudflare in April this year. And since then, we have been building those serverless observability capabilities directly within the Cloudflare developer platform. And today I'm with Kyle.
Hi, everyone. My name is Kyle Galbraith. I'm the co-founder and CEO of Depot. At Depot, we're relentlessly focused on accelerating software builds.
Cool. So I've been working with Kyle and the Depot team for about 2 years now in making their serverless application more observable. And today, I want to tell you a little bit about what are the challenges that come with observing serverless architectures and how you can actually build observable serverless applications. So that's the agenda for today. We're going to start with, what are those challenges? Everybody says observing serverless architectures is hard, but what does that actually mean? What are the traditional methods of monitoring and sometimes observability that, a few people are trying to push to serverless architectures, but they're not quite fit for purpose? So after that, what are our options for actually observing serverless architectures? And it's 2024. We got to talk a little bit about generative AI. How can we use this new paradigm to actually have more observable serverless architectures? I work at Cloudflare, so I'm going to tell you a little bit more about the developer platform and also what we are doing to make those serverless applications easy to observe on the Cloudflare developer platform, such that you don't have to do all this work that we're going to talk about in the beginning, and it's just right there for you. And then after that, Kyle is going to tell you a little bit more about how they have been solving these problems over the past 2 years at Depot. So, serverless applications. What is a serverless application? I think the word serverless has been taken by marketing teams, so it's very hard today to actually know what a serverless application is. And to me, it's actually pretty simple. Can you use those primitives to build applications without having to worry about the underlying architecture, the underlying infrastructure? So I believe there are essentially 3 layers of primitives in the cloud. You have the first layer, which is you manage everything. That's your EC2 instances, right? You sign up, you get an EC2 instance, and everything is up to you. Yes, you don't make sure there's electricity on those servers, but ultimately, those virtual machines, everything in there is your responsibility. The second layer is what you will have in something like Fargate, where you provide a container image, you're still responsible for everything that happens in that container image, but you don't manage the rest of the networking and etc. It just works. The final layer is what I like to call real serverless, where you essentially just say, hey, I want a runtime. I want a JavaScript runtime. I want a C# runtime, and this is my code. Run this for me. I don't want to manage anything else. So I've been describing compute, like that's how it works on the compute layer. But you can do the same thing for databases as well. You can do the same thing for data streaming. You can do the same thing for queues, where essentially you say, hey, I want a queue. I want this throughput. I want it to send events here, and it just works. Now, let's say you have all of these primitives that you can essentially instantiate at will without having to worry about how it's actually working behind the scenes. What tends to happen is that building applications becomes very different when you have those primitives. So you start to have things like this, where instead of having a single server, you have multiple functions doing individual things, talking to multiple databases, pushing events to multiple queues, and having multiple event buses that are coordinating all of those events between the services. It starts really simple like this usually, but you get to here, where ultimately you have all of these boxes that are doing things, but how do you know actually what's going on? How are you actually able to say, hey, A user made a call to this endpoint, and it resulted in this side effect on that other database. It becomes extremely difficult, especially if you're relying on the existing tooling that have been around for, I don't know, Nagios has been around for forever. In my software engineering kind of career, that's forever. So those traditional methods, they rely on what a lot of people call the 3 pillars of observability, which are metrics, logs, and traces. What are metrics? Metrics are essentially numbers. CPU usage, right? Something that you can count, something that you can increase, something that you can get a percentage of. How much CPU am I using? How much memory am I using? How many calls am I getting? How many of these calls are failing? Those kind of things are what you will typically have in metrics. And then you have logs. Everybody knows what logs are. That's the first thing we learn when we learn how to write code. Printf, hello world, console.log, hello world. And then we build the habit of using these strings to actually debug our applications. Whereas these strings are actually not the thing that you want to be able to debug your application in production, especially when you have that myriad of functions and databases all interacting with each other. And then you have distributed tracing. Distributed tracing is a little better than the other two, but it really depends on how you actually use that data. So distributed tracing, what is it? Essentially, when you have a call coming into a service, that service, microservices today, everybody's using microservices, that first service is going to make calls to 2, 3, 4 other services in order to fulfill the request that the user kind of sent in. Now, distributed tracing enables you to visualize the flow of that request throughout all of these services. We are going to dig deeper into that a little bit. But let's look at how logs work. So this is a screenshot of my CloudWatch. I'm assuming that almost everybody has used CloudWatch here. Essentially, you have those strings that are there, and you can search them. But there are fundamental issues with this way of debugging serverless applications. First of all, each Lambda function, if you're on AWS, is going to create a different log group. So now your logs are scattered across multiple log groups, and it becomes very difficult to actually see emergent behavior, how these functions are interacting with each other. The other difficulty really is, how do you send these logs to another provider? I'm sure that some of you guys are using observability providers out there. How do you take logs outside of CloudWatch to another provider? You need to start building infrastructure. You need to start building Kinesis streams. You need to start having Lambda functions processing all those logs and sending them to another provider. And that's more boxes that you need on that insane chart that we saw to get an understanding of that really complex chart in the first place. So yeah, it's all strings. The best thing you could do is basic search. There are some query capabilities these days. If you print JSON logs, structured logs as we call them, you can do some basic querying on there. But it is still very limited in correlating things between multiple functions and multiple databases. How do you observe that? The next step is metrics. So this is a screenshot again from my AWS Lambda dashboard. And metrics here, for example, we have the error count, the success rate, the duration, the concurrent executions, etc. But I want to bring your attention to the very first chart. We can see there that around 9:50, there was a spike in errors. So it went from 0 to 4. And about 5 minutes later, there was also a spike in latency, in the duration of the execution of those Lambda functions. Yes, I know that this metric is telling me something is wrong, like something happened there. But how do I actually know what happened there? I have no way of actually figuring out what caused that spike, those two spikes essentially. Are they even correlated? I don't know. So In these situations, when what you have available to you as tooling is metrics, you start to do pattern matching based on your experience, based on what you've seen before. And I know that this function is processing messages from a Kinesis stream. So my first thought is, hey, that error is probably a poison pill, like a message that was sent into the stream, but it wasn't, in the right format. So processing of that failed, and as a result of that, all the other events, were lagging behind in processing as well. That's my guess, but I have no way of verifying that that hypothesis is actually correct. So yeah, you have static dashboards, you have no correlation, and that's it. So now let's look at distributed tracing. Again, this is a screenshot from my AWS X-Ray dashboard. It's a handler handling data from an SQS queue and doing a bunch of DynamoDB calls. So this is already better. It's telling me, hey, you're doing all of these DynamoDB calls in sequence. You probably want to have them in parallel. And we have the first bar there, which is essentially the cold start of this function, and it was 322 milliseconds. So it's telling me, hey, you have, cold starts that exist, and you can improve your code a little bit. But where this fails is I can see this one request. I don't know if this behavior is across all my functions or only this function. I don't know if it's just this specific invocation or all the invocations. To know that, I need to open 50 tabs and look at each individual trace independently. Where I've seen using this sort of distributed tracing successfully is actually when reproducing issues. So you know that a set of input is going to result in an error. So you then reproduce it either locally or in the cloud, and then you can view the distributed trace for that and see exactly why that happened. But it's very hard to use this sort of distributed tracing to observe applications in production. So yeah, again, no correlation, is way too granular. So yeah, at the end, the three pillars of observability, they don't exist. It's not something that we should be relying on. And now we're going to talk about a few principles that if you follow, it doesn't really matter which format your data is. If you follow these principles, you are going to have, quotation marks, best-in-class observability. So there is a better way. And those principles are high cardinality and high dimensionality. Let's start with high cardinality. So I say high cardinality and dimensionality a lot, and people always say, hey, like, what does that mean? Like, it's not something that you just know. Like, what does high cardinality and dimensionality means? Cardinality is how distinctive or unique data is within a data set. So essentially, the best way is probably to look at an example. Let's start with low cardinality data. So low cardinality data will be something like an AWS region. I don't know how many regions AWS has today, but from looking at the dashboard, it's probably 40 regions, 45, something in that region. So it doesn't matter how many requests you get. If you're using all the AWS regions, the region value, the region field can only take up to 40 or 50 different values. You cannot have more than that. And an example of a high cardinality value then is something like a request ID. Every time somebody makes a request to your service, you generate a new unique request ID for that specific user. Hopefully your application is very successful and you have hundreds of thousands of requests a second. That's hundreds of thousands of unique request IDs per second. So in your data set, in your logs, request ID can take hundreds of thousands of possible values every second. That's a high cardinality value. So here's an illustration. On this example, service, for example, is a low cardinality field, right? You can only have, if you're in a big corporation, 5,000, 6,000 services, but you will always have a different request ID for every single call that gets into your systems. The second thing is high dimensionality. And dimensionality can be seen as the number of possible columns in a database or data set. So we saw previously, about 10 fields in that JSON object. That's a very low dimensionality object. And for a lot of you guys doing structured logs, a lot of people do very low dimensionality structured logs. So you have in your JSON logs, you have message, user XYZ signed up, you have user ID, the user ID, and you have maybe the path. And you have the path that they call. That's 3 fields. That's very low dimensionality. For high dimensionality, we start talking about tens of these fields, hundreds of these fields, and in the most extreme case, thousands of these fields. And it's really easy to see how you can get to high dimensionality. Here is an example. This is not a very high dimensionality object. I just use it because it could fit on the screen and still be readable. You should be having hundreds of these fields. And the question is why? Why do we need high cardinality and high dimensionality? And I'm going to take an example, actually. Let's say you're building an e-commerce app, and then you have a buy button on your application. Every time a user clicks on the buy button, in order to get those high cardinality and high dimensionality events, or some people call them canonical logs, some people call them wide events, some people call them structured logs. But the main idea is, at the end of your request, you should print a really giant JSON object that has every single detail about what happened during that request. So when the request comes in, you take the headers, you take the body of the request, you take the path, you take the query params, all of that you keep in memory. The service makes a call to an authentication service to verify the identity of the user, sends the JWT, and gets back a Boolean authenticated true or false and a user object with all the properties of that object. You keep that in memory. You make another call to an inventory service to check if the item that the user is about to purchase is available. All the details of that call, you keep that in memory. And you do that for absolutely everything that happens in that handler. And at the end, you stringify it and you print it. It goes in whichever observability tool that you use. It doesn't really matter today. The most important thing is to have all of those hundreds, potentially thousands of fields printed. Now, what can you do with that very wide event with high cardinality and high dimensionality data? What you can do is answer pretty much any question about the emergent behavior of your application in production. And this is a screenshot from Baseline, the tool that we built. We're now bringing this into the Cloudflare ecosystem. But the best thing I can do is actually explain to you like a typical flow that a developer will follow when investigating an issue with that data. Let's say customer support messages you on your e-commerce app saying, hey, a lot of users are saying every time they press the buy button, it doesn't work. That's the entire bug report. It doesn't work. And we have all been there. So if you don't have high cardinality and high dimensionality data, how do you even start to investigate that? I haven't done that in a long time, so I don't know how you start to investigate that. But with this, first thing you do is group by all those events because it's a JSON and you have a tool that can actually do filters and group bys and complex queries. You do a group by status code. You see that only 2% of the requests are 500s and the rest are 200s. It's not a big deal. Only 2% of our users are impacted. Now, why are those 2% of users impacted? Like, what you should do next is now look at the raw data. Because in those tools, you still have access to the raw data of the events that were produced. You look at the raw data and you notice that actually all the events that are failing is because they have a specific user agent. And if you're actually doing a lot of work, you can actually also add the Git hash of the specific version that is in production in that wide event. So you can group by that Git hash and see that, okay, this issue started happening at the latest deployment, and it's a specific user agent that is having those issues. Now you can go into your Git repo and see exactly the line of code that created this issue in production. So yeah, you can run advanced queries. You have dynamic dashboards. You can zoom in. Zoom in doesn't mean just making the image bigger. It actually reruns the query with a higher granularity so that you have more insights into what's happening in production. And more importantly, you can correlate. So everything I described so far was just using those wide events. But if in addition to that you have distributed tracing, you can correlate that data with the traces. And instead of visualizing a single trace at a time, you have this scatter plot that is showing you all the traces within the time frame. On the x-axis, you have the time. On the y-axis, you have the duration, the latency of the function. And you can instantly see that there are 3 outliers here, right? Like those 3 dots at the top. There is an issue there. Should we investigate? But we know that it's not a problem across the entire fleet of requests. Also, it's color-coded. So all the greens are the 200s, all the requests that passed. The red is an error. And if you had cold starts as well, it would be blue. So from just looking at the chart, you see exactly what's going on, and you can click on any of these buttons, or of these circles, or in the table below to actually view a single trace and have that same view that we had in X-ray. So you have both high-level view of what is happening across the application and individual view in every single trace. Oops, interesting. What about AI? Let's ignore that first sentence. What about AI? So, again, 2024, AI is changing almost everything. And I think it's important for us to actually think about how we can use this new paradigm of computing to actually make our lives easier when observing serverless applications. So here is a trace again. So we have multiple views for the trace. You have the normal kind of timeline view, but also you have these boxes that are showing you more the relationship between components of your application, which component is calling which other component, etc. But on this specific trace, there's one of the boxes, I think it says durable object async work. There is a red dot there. It's telling me there is an error. Something happened in that box. I want to know exactly what happened there and how can I solve it. Typically, I will have to click on each one of these individual boxes, read the kind of raw data, and figure out what's going on. But these new large language models are actually pretty good at taking a lot of data and synthesizing it into something that is which is easier to digest by humans. And that's what we spent about 6 months building. You can take any trace. You can just say, hey, here is a trace ID, here is a request ID, tell me what's going on here. And it's a bit hard to read, but in a nutshell, it tells me exactly what's going on in this request. It tells me where the error is happening, and it even suggests code that I can then go into my code base and see if I can use that to solve the issue that was happening within that trace. But again, we don't want to stop here. This is, just a few weeks of work. What if instead of giving to the AI model a single trace or a single request, we were able to give the entire set of requests and traces that happened over the past hour? Or what if we didn't even give it ourselves? It just happened in the background automatically, continuously looking at all of these requests, all of these traces, all of these wide events, and telling us, hey, there's something wrong here. Here is a pull request. Do you want to review it? Do you want to merge it? And that's the sort of thing that we're working at Cloudflare on now. So over the past 8 months or so, I've been at Cloudflare. Cloudflare is the only composable internet-native platform. I don't know what that means, but working on the tool, what I know is what we are doing is taking the Cloudflare network that you all know for the CDN and making it the cloud, right? On the Cloudflare network, you have compute and storage at more than 320 cities, and I don't know how many locations because it keeps going up every week. You can deploy your applications in all those cities and have that low latency of less than 50 milliseconds to more than 95% of the world's internet connected population. So we don't want to stop at just giving you compute and storage on the edge. What we are actually doing is building new primitives, thinking those primitives from the ground up. How do we actually make building applications fun again? And I've been having a lot of fun for the past 8 months at Cloudflare, just shipping code, not having to worry about if it's going to work, because the network is taking care of that for me. So you can now build full-stack applications on Cloudflare. You can start with the WAF, the bot management, etc. But we also have compute with Cloudflare Workers, Workers AI. There's, of course, the CDN that we all know. We have a few static content and media services, Cloudflare R2, which is essentially S3 compatible block storage that is available to you on the edge. We have a few data and storage products, Cloudflare D1, which is a SQLite database that is available to you, Cloudflare KV, which is a fast KV store, and by fast, I'm talking less than 10 milliseconds across the world to get data into your application. We have Vectorize, which is our vector database. We have Cloudflare Queues, which is a queue service, again, replicated across the globe. And the more interesting one to me is actually durable objects. Durable objects is a primitive that is available literally only on Cloudflare, and it's possible only because we control the network. Durable object is stateful serverless. Typically, when you call a serverless function, as soon as that function returns, whatever was in memory is gone. With durable object, that memory stays, and you can access it at whatever point in the future. And more interestingly, we recently added a SQLite database right next to the durable object, and you can access it without any additional latency, so it's a synchronous operation. It's a very interesting paradigm to play with and highly recommend. And after that, we have all the observability tooling. That's what I've been working on. Cloudflare Log Push, Cloudflare Tail Workers, Workers Observability, Workers Log, Workers Analytics Engine, etc. But the beauty of it is, this is not a walled garden. You can export any data from Cloudflare to any other provider at any point in time, usually with no extra cost. And you can manage all of it with your favorite infrastructure as code tooling. So yeah, all the things that I showed you about baseline and wide events, etc., we are building that natively within the Cloudflare ecosystem. So all those high cardinality events, etc., and we're actually making it easier for you. So let's say you have your legacy console.log user completed purchase. What we are going to do in the background is add as much data as we can, as many fields as we can to that data such that when you query it, it's available to you. So to that console.log user signed up, we are going to add the name of the function. If it was consuming from a queue, we are going to add the name of the queue. If it was an HTTP request, we are going to add all the HTTP headers, the response status code, all of these things, such that even with no additional effort, you have the benefits of these high cardinality and high dimensionality events. So yeah, I'm going to pass it to Kyle to talk a little bit more about the work they've been doing at Depot.
Awesome. Hello, everyone. Thank you for having me. I'm going to talk a little bit today about how Depot observes its serverless components. But before I do that, I want to give a little bit of context on what Depot is. So at Depot, we're developers who effectively grew annoyed and frustrated with the constant pain of slow builds, both locally and CI. So we got so fed up about 2.5 years ago that we went and built the solution we had always wanted ourselves. Today, that solution is Depot. We can make a software build up to 40 times faster. We focus on 2 areas currently. There's our initial product, a remote container build service, where we offer instant shared layer caching and native multi-platform image builds for both Intel and ARM. We also offer a suite of optimizations to accelerate image builds both locally and CI, and insights into your Docker image builds. Our recent launch is Depot Managed GitHub Action Runners, which brings all of the performance of Depot into the entire CI workflow. We run EC2 instances that are optimized to boot quickly for every job via our own orchestration and auto-scaling system. Our runners are up to 10 times faster. We ship them with 10x faster caching, and they're half the cost of GitHub hosted runners. We're really relentless about build performance, and it's reflected in the tools that we offer, but it's also reflected in how we monitor those tools, which is what I'm going to talk about today. So a core part of our internal build architecture is EC2, so not serverless. And a reason for that is largely because a GitHub Actions runner and a Docker image build assume that they have an entire VM with root privileges. But outside of the actual builder compute, we use a lot of serverless components to stitch everything together. So on the left-hand side is a simplified view of the components inside of AWS for moving a request for a build into an actual running EC2 instance that starts in less than 5 minutes. We have our control plane, which lives in Fargate. The control plane receives various events that tell our orchestration system about new states or new requests for compute. Those messages are then packaged up and shipped down to SQS queues. Our orchestration system lives inside of Lambda. It reads messages off of SQS and reacts to requested operations like launching new EC2 instances, stopping instances, moving instances from our warm pools into active instances, and killing machines when builds are terminated. The actual builder compute itself lives inside of EC2, like I said before. On those machines is a process running that is effectively communicating with our orchestration system. That process is told what to run on the machine, whether it's a GitHub Actions job or a container image build, whatever it might be. On the right-hand side is where we have our serverless components inside of Cloudflare. So as you can see from this diagram, we essentially have serverless components that span providers, which is not super common, but for Depot, it's necessary. And why is it necessary? On the Cloudflare side, we essentially use Cloudflare workers and Cloudflare R2 to essentially serve our registry product. So where they connect is we have Lambda at edge running behind CloudFront that detects if a request for an image from our registry is coming from inside of AWS, aka on one of our GitHub Actions runners. We redirect that request to S3 because we can serve it quickly. The network latency is fast. We don't have to worry about costs, things like that. However, it's a registry product. People want to pull their Docker images from things outside of AWS. So in that model, we essentially detect that scenario inside of Lambda at edge, and we redirect the request for the pull to R2. So we have a lot of moving pieces to our core architecture, and we have pieces of that span multiple providers. That said, the problems we have with observing the serverless components of Depot really boil down to performance, tracing, and viewing everything through a single pane of glass. We need to be able to easily spot bottlenecks going across different services and even different providers. We need to know where things might be broken in the chain of requests. We need to know if we're meeting our own internal expectations for different parts of the system. We have several services, like I said before, running inside of AWS Lambda, other services running inside Cloudflare workers. In scenarios like supporting our registry, we have a mix of both. And unlike a VM or container where we have one piece of compute, as Boris said earlier, we could have hundreds of thousands of isolated pieces of compute in a 5-minute window. In that kind of distributed system, one of the hardest problems is being able to spot where the bottlenecks are. For Depot, we monitor overall latencies across our serverless components. We know how long a particular Lambda or Cloudflare worker should take given the task it's operating on. So we alarm if we have inconsistencies or issues that break those expectations. Boris talked a little bit earlier about cold starts. I can assure you cold starts are still very real. And they're also one of the more interesting bottlenecks. It's one level before our request latency monitoring, and something we watch to make sure we haven't doubled or tripled our cold start latency, and thus break our earlier assumptions about execution time for a given function. Cold starts are quite interesting because you can unexpectedly grow them just based on what you might be installing into your environment. So this is something that we watch very closely. With traditional observability, we can just go check the logs and see where things are in a VM. But with our serverless workloads, we have to look across several different log streams, across hundreds or thousands of invocations, and that's just for one Lambda function. We have services that pass through multiple functions with Depot, and even across providers, like we saw in the reference architecture. So you really need an observability tool that lets you see everything through one pane of glass. Here we can see the errors of different services inside of the Depot components we talked about earlier, and drill in on each one when we need to diagnose things further. It's incredibly helpful to have a view like this because for services where there is multiple functions across multiple providers, we really need to know which step in the flow is having problems so that we can go figure out what's broken. One of the things that we work very hard on with Depot is we're relentless about build performance. We work hard to squeeze out as much performance as possible to make builds exponentially faster. To do that, I would venture to say that we have some of the strictest internal SLAs on ourselves about latency and performance. So we leverage observability tools and OpenTelemetry to monitor and alert ourselves if our performance has degraded to an unexpected level. So again, Boris talked a little bit about this earlier. We start at the highest level. Our target, in this example, we're looking at one of the key pieces of our GitHub Actions runner product. So when you go to run a GitHub Actions job, GitHub sends us a webhook. We then need to bring a runner online, which in Depot parlance is effectively an infrastructure stack. We need to bring that runner online within 10 to 30 seconds, and we have a series of tasks that are running to assign infrastructure to that job. The longer it takes to assign infrastructure to that job, the longer a GitHub Actions job is queued, the more annoyed developers are. So again, we start by monitoring at the highest level. What's the duration of those tasks? Are there any outliers? And when there are outliers that break our assumptions between 10 and 30 seconds, we alert ourselves. So we see here that we have an outlier of 50 seconds. We can drill in on this outlier inside a baseline to understand what happened. We use OpenTelemetry to get insights into what was that task doing at that time. We can see it took 50 seconds. We can see some of the internal bits of this task, which is effectively a control loop, where we're consistently looping over and over again to find an available infrastructure stack and give it to the pending runner. We can see multiple runs through the loop over and over and over again, effectively showing us that we were failing to grab an infrastructure stack and assign it to the runner. This kind of starvation tends to point out either a capacity issue in our pools of compute or the infrastructure stack that we were bringing online was being stolen by another job. In this example, it ended up being the latter. And so we implemented some strict ordering with SVS FIFO to reduce the likelihood of it happening again. This level of observability into our serverless components makes a massive difference in operating Depot on a day-to-day basis. We effectively are able to monitor the performance of not only Depot, but also the underlying infrastructure providers that we're using. We're able to see everything through a single pane of glass, and we're able to alert ourselves if any issues arise. I'll kick it back over to Boris to close things out.
Thank you. So yeah, as we could see there, the main idea behind great observability is that you stop guessing what's wrong with your application. You're just able to see it right in front of you and know exactly where the issue is and how to fix it. With traditional observability, you spend so much time guessing and pattern matching. We want you to adopt those principles of high dimensionality and high cardinality, because with them, the guessing game is essentially over. Thank you very much.